Hi guys, welcome back to my channel. So in this video I'm gonna go over some questions of the past final that I found online. So let's get started. So the first question we have over here, for the propositions P and Q, the statement P implies Q is logically equivalent to which of the following? Okay, so we need to choose the P implies Q is equivalent to which of the following. So for that you guys can create a truth table. Okay, so if you create a truth table of P and Q, okay, and you do P implies Q, so P implies Q, you guys already know if it's true, if the P value is true and the Q value is false, so the true implies false, that always gives false, and the rest you're just gonna write true. Okay, so just remember, for P implies Q, every time you have T implies false, the answer is false, but the rest of them it's true. Okay, so that's how you create for P implies Q. And for negative Q, that's what you call the contrapositive. Okay, so the negative that is negative Q implies negative P, or you can just say not Q implies not P. So here you see not Q over here. So if you create the truth table of this one, you guys see the truth table is exactly the same for this one and for this one. So which means that P implies Q is logically equivalent to not Q implies not P. Okay, so you guys can simply memorize it or make a truth table in the exam, but whatever works for you. But I would just say just memorize it. Okay, so we know that P implies Q is logically equivalent to contrapositive not Q implies not P. Okay, and similarly here we have for propositions P and Q, the inverse of P implies Q is logically equivalent to. Okay, so now we want to find the logical equivalence of the inverse. So like we can see in the table over here, so the inverse is always like if you have P implies Q, right? So if you want to find the inverse of this, so just put a negative sign in front of both predicates, so that is your inverse. Okay, and if you wanna find the converse is simply you're gonna swap P and Q. So if you write Q implies P, that is your converse, and if you write not Q implies not P, that is your inverse. And if you compare the truth table of these two, of the converse and the inverse, you guys see it is exactly the same, which means that the inverse is equivalent to the converse. Okay, so here we know that the inverse is equivalent to the converse. So which option does it belong? So that's option number D. Alright, so next question. We have for proposition P and Q, the converse of P implies Q is logically equivalent to. So like I explained over here, the converse and the inverse, they are equal to each other. So here if they're asking for the converse, which is equivalent, the converse of P implies Q is equivalent to, so here the answer would be not P implies not Q, right? Because the converse is logically equivalent to the inverse. But here you guys see in the option you don't have any inverse over here, but the converse is also logically equivalent to itself, no? So what is the converse then? It is Q implies P, and we have over here Q implies P, so that is the option over here. Okay, so make sure you guys know this very well, because when I did the exam it did show up in the exam the exact 3 questions, so make sure you know how to do them or just memorize the answer. Okay, so for this one we have considered the statement P implies Q, Q therefore P. Okay, so this is like the statement written as P implies Q, and you have Q, and then this statement over here, this thing simply means like therefore P. Okay, so this is how you read it. So P implies Q, Q therefore P. So is this correct? Okay, in order to determine this, you guys have to know the modus ponens and modus tollens. Okay, so for modus ponens, you guys just need to remember that for modus ponens, it's always P implies Q, P therefore Q. Okay, so like simply like you know, if it's P implies Q, so if you have P, so then it's gonna be Q. Okay, so you can just like, it's like a trick. Okay, so you can simply like put an implies over here, so you know if it's P implies Q, so that has to be P implies Q as well if it's Morse's tollens. Okay, but if it's Morse's tollens, so like I said in the previous questions, that if you have P implies Q, which is equivalent to not Q implies not P contrapositive, right? So for Morse's tollens, you have to remember that it's P implies Q, and for Morse's tollens, you just remember that it's contrapositive. Okay, so P implies Q, not Q, therefore not P. So that's for Morse's tollens. Okay, so if you have anything other than these, a Morse's tollens and Morse's tollens, so then it's gonna be either a converse error or an inverse error. Okay, so let's see. So here we have P implies Q, and then we have Q, therefore P. So Q, therefore P. If you try to put an implication sign over here, so what does it become? So it becomes Q implies P, and P implies Q, and Q implies P. And what is it? It's a converse, right? I just explained you in the previous question that Q implies P. If you just swap the values of the predicates P and Q, so it becomes Q and P, which is known as the converse. So that means this is not Morse's tollens, this is not Morse's tollens, this is not hypothetical syllogism. It is what? It is a converse error. Okay, so similarly for this one, consider the following: P implies Q, not Q, therefore P. Okay, so here we have P implies Q, not P, therefore not Q. Okay, so if you put an implication over here, so what does it become? So it becomes not P implies not Q. And what is this known as? So not Q implies not P. It is an inverse of P implies Q, so which is not Morse's tollens, not Morse's tollens, so that is known as an inverse error. Okay, so which option does it correspond to? The inverse error. And it is always it is always going to be a non-validating pattern because we cannot validate it. Okay, and if you're wondering why, then I'm gonna make another video on this explaining why it doesn't work, so make sure you can check that out. Okay, so we are given all these letters over here, and we're asked that these are considered to be well-formed formulas. Okay, and if we only have a dot and we consider it to be any connective, and we need to determine which of the expression is not a formula. Okay, so a connective can be anything like an or, and, or anything you want, implies, or whatever. Okay, so let's just say if it's an or. Okay, so here, so we need to make sure if it's a formula or not. Okay, so here, if this is or, so if we have, wait, it's too thick. So if we have something like this, is this allowed? Yeah, it's allowed. Why not? So here, if we replace this with or, and or, is this a valid formula? Right? Because here we have or and then or. It does look valid, right? Yeah, so that's valid, that's allowed. And here that is already a valid formula over here because it has and predicate, and in between two predicates, and here we only have or in between two predicates and or here, right? So these are allowed. And what about this one? Are we allowed to put a not? Yeah, why not? Okay, so this simply means like we have one not and then we put another one, so this is gonna cancel out this one, right? And we have another one then, so then this thing is gonna be equal to only one not. Okay, so this is allowed as well. But here, okay, so here we just gonna replace this with or. Okay, so then this becomes this. Okay, but are we allowed to put a negation after the predicate, no, that's not allowed in formulas, right? So that is the wrong formula, because we have a negation after the predicate. We cannot have a negation after the predicate. We always have it before the predicate. Okay, so that is the wrong answer. This is the one that is not a formula. Okay, so for proposition P and Q, the statement P implies Q is a, okay, so for this one we need to create a truth table. And for truth table, you know, to create the truth table, if we have the predicate P, so for the predicate P we can have a true value and a false value, right? It can be true or false. So if P is true, so then the Q, it can be true, and if the P is true, it can also be false. But if the first P turns out to be false, then the second Q, it can be true or it can either be false. Okay, so that completes our truth table. So for P and Q, so if we have a first one as true, the P, so the Q we can have true as well. So true, 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 false, then false, true, and false, false. Alright, so that completes it. These are the possibilities we can have for P and Q. And now we need to find for P implies Q. So for P implies Q is like I said before, every time we have T implies false, so that is gonna be false. Okay, so we have P implies Q, which is the value of T is equals to, the P is equals to true, and the value of Q is equals to false. So every time we have something like this, T implies false, the answer is gonna be false. Okay, so you're gonna put a false here, and the rest is always true. Anything other than this, T implies false, it's gonna be true. Okay, so that is not a tautology. Tautology means the truth table. If you create the truth table, so if it gives you, wait, use another color. Okay, so if it gives you all true, 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 that means it's a tautology, but which is not the case over here, so that's not a tautology. Contradiction means the inverse simply. Okay, if you have like false, 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 if you create the truth table, that means it's a contradiction, which is not the case over here as well. And contingency, so contingency means a mixture of true and false, which is of course the case over here. We have true and we also have false, so that is a contingency. Okay, so here P, for the proposition P and Q, the statement P if and only if Q implies, okay, so for this one, you guys have to know this from discrete math, that if both of the values are true, only then the statement is true. Okay, so these have to have the same truth value. Okay, so here yeah, so that it's gonna be an option C, because it says when P and Q have the same truth value, then it's true, otherwise it's false. And that's how you do it. And yeah, I remember this question was in my exam as well. If it's not clear for you guys, then I don't mind doing the truth table of it, but I mean, you guys I think already know it from discrete math, but yeah, let me just make a truth table if it helps you guys. Okay, so here the possibilities of P and Q, they're gonna remain the same: true, true, false, false, true, false, true, false. Okay, so P if and only if Q, so it means every time they have the same truth value, we put a true. So you see, they have the same truth values, we put a true, otherwise we put a false. So that's how you do the truth table of P if and only if Q. Okay, so yeah, just make sure to know it. Alright, so let's use some logic over here to solve these. Okay, so here it says if one is the Prime Minister of Canada, then one must be 35 years of age or older. Okay, so this is simply an if and then statement. So here we have if over P, and this is our Q. Okay, then here it says this in todo is 35 years of age or older. Okay, so we just replace the one with the name over here, so it's nothing but it's simply the same thing as Q. Okay, so this statement is our Q. So then we say therefore Okay, so just so that it doesn't confuse you. Okay, so therefore Justin Trudeau is the Prime Minister of Canada. Okay, so here again we replace the one with the name, but it's still the same statement, P. So what do we get? So the above statement, we have P implies Q, because we have if and then, right? So we have P implies Q, and then we have Q, and then later we have therefore P. So here, like I said before, here if you cannot visualize it, so just put like a arrow over here to read it, so it becomes Q implies P. Okay, so it becomes Q implies P. And as I already told you guys in the previous question, if you have if you're swapping P and Q, so that is the converse, and it is not the modulus ponens and tollens, it is a converse error. So the correct statement here is E. Okay, so here we have in wish you were here. It's a song or whatever. Okay, swimming in a fishbowl. If we take the sentence, some people are lost souls, and we let P of X to denote X is a person and Q of X to denote X is a lost soul, then sentence translate to. Okay, so we are assuming here, if we have the sentence some people are lost souls, okay, and we're denoting P of X to be X is a person, and Q of X to X is a lost soul. Okay, and here because it's saying some, okay, and you already know for some it looks like this, okay, and because this is read as for all, okay, so you're just gonna cancel for all. Okay, so you're only left with B and D over here. Okay, and here if you try to translate this, P implies Q. P implies Q means if it's a person, then it's a lost soul, and in this case you always put for all. So if you have like all people are lost souls, then this would be correct. But here, since you have some people are lost souls, for some you're always gonna put an and. Okay, so if it's a lost soul, if it's a person and it's a soul, so that means there has to be some people in this domain, some values of X for which we can say that it belongs to the domain. So this whole thing, it's gonna be read as some people are lost souls. Okay, so I hope you guys got it. Okay, if not, let me try to explain it again. So some people are lost souls. For some, you already know it's this one, because for all it's like this. Okay, so every time you have some, you know it's this one, or also when you have like there exist, so you have this one as well, and with this one you're always gonna put an and. Okay, for this one you're gonna put an implication, but for this one it's always gonna be an and. So yeah, so this is your answer. Okay, so here we have the formula for all y there exists and x likes xy. Okay, so we have likes xy. Okay, so we have likes x and y, which means x likes y, right? But here we are given that for all y there exists an x. Okay, so which means basically for every value of y there's at least an x. Okay, so let me give you like an example. So if for y values, okay, x likes y. Okay, so here the domain of y we have over here, let's say we have a, b, c in y. So for every y, a, b, c, there exists at least someone from the x. Okay, there exists at least one person in the x who likes y. Okay, so which means the y is being loved because it is written y first, right? So we need to make sure we write in the form of y and not in the form of x. So if we write it in the form of y, which means y is being loved by some x. right? Okay, so if we try to write it, every Y is being loved or liked, whatever you want to say, by some X. And if you try to like generalize this statement, so you can say everyone is liked by someone, because everyone is like everyone in Y is being liked by some X, right? So everyone liked by someone. So yeah, that's the correct statement. Okay, so we have here for this statement, all people are honest, identify a contradictory statement. Okay, okay, so all people are honest. So first we need to write it in terms of predicate logic. Okay, so as I told you before, every time we have all, that means an implication. Okay, all people are honest means if it's a person, then it's an honest. Okay, so we can imply P to be a person, and then H to be honest. Okay, and you want to say all people are honest, we can say if it's a person, then it's honest, and that is the case for all X's in the domain. Okay, so this reads as all people are honest. Okay, and if we want to contradict the statement, which means we're putting a negation in front of it. Okay, so if we're putting a negation in front of it, so it's going to multiply it, so then this all, it's going to turn into there exist. Okay, and yeah, and you guys have to know that if you have P implies Q, like here in this case P implies Q, which is P implies H here, okay, so here every time you have this can also be written as not Q or P. Okay, so here before multiplying by the contradiction, we can simply write it in this way: P implies Q, so it can also be written as not P or Q. So it's easier for us to contradict later. Okay, so once we have this, now let's go ahead and contradict it. So okay, so then this becomes there exists an X. Okay, there exists an X, and then this negation, it's gonna cancel out with this negation. Okay, so we're only left with P of X, and if we multiply the negation with an OR operator, so that is I think the rule is I don't remember the rule name. I think Moses Bones, no, I forgot the name, it doesn't matter, but here it has to be an AND. Okay, so if you're multiplying a negation with an OR, so it becomes an AND, but if you're multiplying with an AND, so it becomes a OR. Okay, so that's what you have to know. And then this is gonna be multiplied with the Q, so then you are left with the statement P of X and not Q of X. So if you try to read this statement, what is it? It is person and not honest, and that is the case for some people. Okay, so some people are not honest. So that is the statement. Oh, sorry, it means are honest. Some people are not honest. That's number 8. Okay, so yeah, I remember I had like 5 to 6 questions in the exam about this, so make sure you know these very well. Okay, for the statement some people are honest. Okay, so some people are honest. So if people are honest, first try to write this. Okay, so we can say people, okay, person, P of X, and each of us as honest. So if it's a person, so it's honest, so we just gonna write an AND. Okay, so it is read as, so okay, you can read it as person is honest. Okay, so and that is the case for some, so we can write it as there exist. Okay, so this is read as some people are honest, because this is read as people are honest, and this means there exist some people who are honest. So if you read it all together, some people are honest. Okay, so and we need to find the subaltern of this one. So for superaltern. So for the superaltern, this statement itself is a subaltern. The subaltern means every time you have like some, so that is subaltern. But if you want to know the superaltern, it's gonna be the same thing but within all. Okay, so you're gonna make the statement this exact same thing, but instead you're gonna replace the some with the all. Okay, so all people are honest. So here we do not have any option which says all people are honest. Okay, so what they did is they just put it the other way around, because if you're trying to say all people are honest, so just think about it logically. All people are honest, what are you exactly trying to say? You're trying to say that there's no one who cheat, right? Because everyone is honest. So that is what you're trying to say, right? No people cheat. So yeah, this is like a little bit tricky type of question where they're just trying to trick you. So all people are honest, which is exactly the same thing as no people cheat. Okay, so here as well, here it says for the statement no people are honest, identify the contradictory statement from the below. So for the contradictory, you guys have to know how to write in this form. Okay, so here no people are honest, so this statement is gonna be equivalent to the statement with an all. Okay, so you can write this statement as if no one is honest, so this statement is equal to that everyone is honest, right? So everyone is honest, or you can say all people are honest. So if you're writing all people are honest, so in order to write it, if it's a person, then he is honest, she's honest, and that is the case for everyone. Okay, so this is read as all people are honest. And then if you want to contradict it, so we're going to put a negation in front of it, multiply the whole expression with a negation, so it becomes there exists an x, and of course this one, remember, we need to put this as p, not p of x or h of x. Okay, so then if we multiply this, negation times negation, so then this becomes p of x, this negation times or becomes and this negation times h, so it becomes h, negative h. So now we have, if it's a person, then he's not honest, and that is the case for some people. So some people are not honest, which is some people are not honest, which is option number B. Okay, here we are finding the subaltern. Subaltern, I told you it's with some, start with some. Okay, so here already you know that it's gonna start with some. Okay, for the statement no people are honest, so it is the same thing as here, so you can translate it, you already translated all people are honest. Okay, so this is gonna be translated to all people are honest. So for subaltern, you're just going to replace the all with some, so some people are honest, some people are honest, that is the letter C. Alright guys, so let's solve this question. Here it says let p of x denotes x is a person and q of x denote x cheats. Okay, so we have these letters over here, and in the first question we're asked to find the pairs of contradictory statements. Okay, and for this, like I said, you guys, if you guys want to contradict this, so you're just gonna put a negation in front of the statement. Okay, So here you have px implies q, which I told you before can also be written as not q or p of x, right? So px implies q, which can also be written as not p or q. And then we have for all x, okay, and we're putting a negation in front of this whole thing. So if we do that, what does this give us? So then this for all x becomes there exists an x, and this negation and negation cancels out each other, leaving us with p of x only. And then this or becomes into and here this not is gonna come in front of q of x. So that is the statement we get. Okay, and if you want to read it out, so here it says x is a person and x cheat, right? So if it's a person, then it's cheat, and that's the case for everyone, so everyone cheats. And here it says some people do not cheat. Okay, and here let's contradict this one then. If you want to contradict this one, so we are putting again p of x or q of x because it's implied. Okay, and that's the case for all, but here we have a negation already with the q, so we're going to put that here. So then if we multiply, that's going to give us there exists x, and then again the negative comes in front of p, changes into and here this is important, there is already a negation here, so negation times negation, that's simply q of x. It's going to cancel out each other. So here the opposite of this one turns out to be, because this one is all people do not cheat, so then this becomes wait, why did I put a neg? Sorry, yeah, I forgot here. It had to be you have to put a negative over here because it was px or q of x, so then here it has to be a negative here. So here negative cancels out, so here we shouldn't have anything. I'm sorry. Okay, so here then this is going to be translated to all people some people do not cheat. Do cheat, sorry. Yeah, some people do cheat. Okay, so you want to find the pairs over here, right? So here if you guys see this, if you try to contradict it, so it is equal to this one. So this thing that we find over here, do you guys see it over here, right? So this thing matches with the number 4, right? So that means these two are contradictory statements, so 1 and 4. So you found one pair, which is 1 and 4, and let's try to find another one. So if we were trying to contradict this one, we got this thing. Okay, so this statement matches with this one, right? So that means these two are contradictory as well. So we have 2 and 3 are contradictory as well. So do we have an option that correspond to this one? So 1 and 4 and 2 and 3. So that's gonna be your letter B. So that's the answer for this question. So let's move on to another one. Okay, for contraries. Contraries, let me explain after, but let's do subcontraries before. Okay, subcontraries means that two statements can be true at the same time, but they cannot be false at the same time. Okay, if you have some sort of statement, so both of those statements can be true at the same time, okay, but they cannot be false at the same time. Okay, so just remember this for contraries. Okay, so here let's try to find two statements that can be true at the same time. Okay, so like they go hand in hand. Okay, and for this, if it makes easier for you guys, so you can simply write the statements over here in English, so it's easier, you know. Okay, so let's go ahead and write for the first one, so that it's gonna be all people cheat. Okay, and second one is all people do not cheat. Third one is some people cheat. And the fourth one is some people do not cheat. Okay, so we have these statements. So let's go ahead and verify for 1 and 2. Do they make sense altogether if both of them can be true at the same time? 1 and 2. Okay, 1 and 2. All people cheat, all people do not cheat. No, that doesn't make sense. Like, if all people cheat, then all people do not cheat. They cannot be true at the same time. So that option is wrong. And 1 and 3. Okay, 1 and 3. All people cheat, some people cheat. No, it's saying everyone cheat, but at the same time saying some people cheat. That doesn't make sense as well. And then we have 2 and 4. So 2 and 4. All people do not cheat, some people do not cheat. That's like saying the same thing. But like if you're saying everyone do not cheat, but at the same time you're saying some people do not cheat, so like you have to choose everyone or someone. So now this one is no as well. So you're only left with the last option, which is of course the correct answer. So let's try to make sense of it. So 3 and 4. So 3 and 4. Some people cheat and some people do not cheat, right? So it makes sense because some of them cheat, some of them do not cheat. So yeah, these two make sense together. They can be true at the same time. Okay, so here that's the case for 39. And if I want to do contraries, so contraries is like the opposite of the subcontraries. In the contraries, two statements can be false at the same time, but they cannot be true at the same time. Okay, so here you're gonna follow the same procedure that I did over here. Okay, so if you do that, so this should give you option A. 1 and 2, all people cheat and all people do not cheat. Okay, so I'm leaving it for you guys to figure out how I did it. But like if you guys still cannot figure out how I did it, so let me know just in the comments below and I'll try to explain to you guys. Okay, so question 40, which says determine all the pairs of superaltern and subaltern statement. Okay, so superaltern means it starts with all, and subaltern means with some, right? Okay, so here these for the first one we have all people cheat, so that is a superaltern, and we want a pair of super and sub. So that so then this, if you just remove all and replace with some, so that is going to be some people cheat. So do we have something like this? Yeah, some people cheat. So we have 1 and 3 as pairs for super and sub. 1 is super because all people cheat, and you're just removing the all with some, so it becomes some people cheat. So these two are pairs of super and subaltern. And what about the rest? So the next one, you have all people do not cheat. So if you just remove the all and replace it by some, so that becomes some people do not cheat, and which is equivalent to the letter 4, which is 2 and 4. So these two are pairs as well of super and subaltern. So this corresponds to the option number, the letter number C, right? 1 and 3 and 2 and 4. Okay, so that's the correct answer. Let's move on. And yeah guys, I forgot to mention that these questions are very important for the exam because they did show up in my exam, but here it's like a person cheats and it's a person. In my exam we had something like X is gold and X is glitter. So yeah, but the questions were pretty similar, so make sure to practice well with them. Okay, so these questions, they're very simple. Okay, X is a bird and X is a white. P of X denote X is a bird and Q of X denote X is white. So all birds are white, so that is really easy. So if it's a bird, then it's white, and that's the case for every axis in the domain. So that matches with letter D. Okay, some birds are not white. Okay, it has not, remember. Okay, so some birds, forget some for now. Okay, we're just gonna write birds are white. Okay, so sorry, end. Okay, so this translates to some birds, translates to birds are white. But if you want to put not white, so we're just going to put a not in front of it. So some birds are not white, and that's the case or some birds. So that matches with letter C. Okay, let's go ahead and solve this one now. So we have so here we have set A and B, and we have a mapping of like this. Okay, so this is like a set A, and we have set B. Okay, and then in set A we have 1, 2, 3, right? In A we have 1, 2, 3, and in B we have A, B, C, D, and 1 is mapped with D, 2 is mapped with D, and 3 is mapped with C. Okay, so we have something like this over here, and we need to figure out if it's injective, surjective, or bijective, and total and partial. Okay, so let me explain each of these guys to you. Okay, so if a function is injective, so injective, in other words, it's onto I think it's one-to-one. Yeah, so that basically means if you have a function, okay, here, so you have something like this. So here in the injective, you need to make sure that no two axes are mapped to the same y. So if you're having like two values from here are mapped to the same value of y, so that means it is not injective. Okay, so yeah, just remember this definition: no two axes are mapping with a single y. Okay, so here you guys can see that two values of x are mapping to the same y, so that means it's clearly not injective. Okay, so we can write here not injective. Okay, and for surjective, if you guys want to know if a function is surjective, which is also onto function, okay, for surjective, here it is nothing but it is very simple that all the values in the codomain, this is the domain and this is the codomain, right? So all the values in the y have to have something corresponds to x. So every value needs to be mapped with some value. Okay, you cannot leave a value alone. So here, for example, I didn't map anything with D, so if it's left alone, which means it is not surjective. Okay, if you have used everything in the y, which means the codomain, if you have used everything in the codomain, which means it's surjective, but if you have missed a few of them, which means it's not surjective. Okay, so here, are we missing anything? Yeah, so here A and B are not being mapped with anything, so that means it's not surjective. Okay, and what about the partial and total? So for the partial and total, for partial, where's partial? Okay, yeah, partial and total. So partial simply means this is the domain, right? The domain, and this is the codomain. So if you're using all the values of the domain, which means it's a total function, if you're using everything that belongs to the domain. But if you're using some of them and some of them are left alone, so that means that's partial. You're partially using the domain. If you're using all of them, so like total domain, so that's a total. So here in the domain we had 1, 2, 3, and we used all of them, so that means it's a total function. Okay, so here this corresponds to the letter B, right? A function is total, not injective, and not surjective. So that's the correct answer. And yeah, if you guys want to know if it's a function or not, that's pretty easy, because remember, if it's like a function, so here if you're like drawing something, okay, so if you have something like this, no, let me make a circle. Okay, so if you have something like this, so if you just draw a line, so you see there are two dots, because here one x value is corresponding to two y values. One x value has two y values. That means it is not a function. So every time you have something like this, which means it's not a function. Okay, so if you want to see it over here in the form of sets, so if you have 1 2 3, let's say x y z, so every time you have one x value having two y values, so this x value is mapping with x and z as well. So here one x is mapped with two y, that means it's not even a function. Okay, so but when one x value when two x values are corresponding to the same y value, that is not injective. But when one x value is corresponding to two y values, that's not even a function. Okay, so yeah, so just make sure to know all these things. So let's move on. Okay, so we have this question over here which maps the model of the car with the make. Okay, so here we have the list over here of the mapping. So here we have the question which says the expression blah blah blah, and here we have the symbol over here the car would produce. Okay, so here for this you guys have to remember, okay, so if you have something like this, so here they're asking for the domain. So here's how I remember it, because you know the capital D, so the capital D, it looks like this, right? It looks like this thing. So I just remember it, if every time they're asking for this thing, so we're asking for domain. Okay, but if you flip it, okay, if it becomes like this, so that means we're asking for range. Okay, but sometimes it's, so yeah, sometimes we have something like this. Okay, wait, let me try it again. So we have like a line in the middle of it, so this means remove it. Okay, this means like find the domain or the range. This means remove the domain or the range. Okay, so in that case, when you have something like this, so in this case it would be the inverse of this one. So here this thing is domain, right? So then in here this thing becomes the range, and then this thing becomes the domain, like remove from the domain and remove from the range. Okay, I hope you guys understood. That's how I remember it. If it looks like a D, so we're asking for domain. If it's like the inverse D, so that's the range, and it's the inverse of these in the remove. Okay, so here we're asking for what? We're asking for the range of these, right? So we're given the domain, we're asking for the range of these. Okay, so what are these? So we have this one, so the range would be Jeep, and then we have M3, which is BMW. Okay, so that this thing would produce okay, so it will give you and then you have this. Okay, so that is going to be your final answer, because you will not only get the range, but instead you will also write the domain corresponding to the range. Okay, so here the final answer to this is letter C. Let me just put it over here so it's better for you guys to see. So here I just put the answer over here, so that is the correct answer. So this is how it should be written. Okay, okay, so we're gonna do the same thing over here. Okay, so we have here this is D, right? Because it looks like a D, so we're finding the domain over here. So we're finding the domain of BMW. Okay. Okay, so here I wrote the list of the car over here. So here you guys look at the domain for the BMW. Okay, so the domain for the BMW would be this M3, X3 and Z4. Okay, so these are so everything that corresponds to this is gonna be your answer. So here in this case we have here you see M3 BMW X3. So this is your final answer, because you're not only writing the domain here. This is not your correct answer. You also you're going to write the pair that corresponds to it. Okay, so here in this case the letter B is your final answer. Okay, so we have this over here. So here, like I said before, so if you have this expression over here, which means remove, right? So here this is domain, this is range. So what is this then? If this is domain, so that means this is remove range. Okay, so we are but here we have the opposite. So here we are removing the domain. So we're removing the domain that corresponds to these values. Okay, so we're removing this thing, we're removing this, removing this, this and this. Okay, and like I said before, when we're if we want to like find the domain, so we don't only give the domain, we put the pair of it, right? So just like that, we're going to not only remove the domain but also the pair that corresponds to the domain, because if there's no domain, then the range cannot be alone by itself. You have to remove that as well. Okay, so just gonna remove the whole thing, and what is left is your answer. Okay, so here in this case your answer would be letter C. You see, you're left with this, this and this, and that is your answer. Okay, now for next question we are removing. So what are we removing over here? So we're removing the range over here that corresponds to Toyota. Where is it? Okay, yeah, so we are removing the range over here. This, oh, that was Nissan, sorry. Nissan, BMW. Oh yeah, so there are three, so you're gonna remove all of them. Okay, and now we're gonna remove the whole pair. So what are we left with? We are left with these three, and that is our answer. Okay, so that corresponds to letter D. Yeah. Okay, and then we have this, which basically means you're going to override it. Okay, so here you're going to override this. So if you have this Corolla, so you're going to override it with this one now. Okay, so here you have had before Corolla Toyota, so you're going to replace it with Lexus. Okay, then we have M3, so you're going to remove this BMW and you're going to replace it with, okay, and then we have, so that's what you're basically doing over here. Okay, so your final answer, it's gonna remain the exact same thing, but you're just overriding this. Okay, so then here your final answer is not one of these options, is letter E. Let me show you guys over here. So yeah, that is your final answer there. Okay, and I think similarly you guys can solve the other questions because they're pretty straightforward. Okay, so yeah, I just explained you guys how to do it. So these are the answer to it, and I think it's gonna be really easy for you guys because we're just basically repeating the same question over and over again here. Okay, so here we are replacing, remember. Alright guys, so let's solve some temporal logic problems. Okay, and this part is really important. You guys have to make sure that you do a lot of problems of temporal logic, because when I did the exam there were like 100 MCQs and 30 of them were only on temporal logic. So yeah, make sure you guys know this very well. Okay, so here the first question is we need to find the formula for the invariance. Okay, so for the invariance, you simply have to memorize it, that for invariance it is this one. Okay, so this this is used for always. Okay, so every time you have this always thing, that is named as the invariance property. So just memorize it, you don't have to worry about this much. But yeah, this exact questions were in my exam, I remember. So yeah, just memorize them. And for the guarantee property, it is always on the eventually one. Okay, so every time you have something like this, which means eventually, that is the guarantee property. All right, so let's move on. Okay, and for the recurrence property, again you have to memorize it, and this was also in the exam. It is recurrence, you can remember it like the always and eventually. Okay, every time you have like always and eventually together, that's the recurrence property. Okay, so that's gonna be this one. And then the stability is, it's like the inverse of the recurrence. So every time you have eventually always, so that is gonna be your stability. Okay, so yeah, again very important to memorize these. Okay, all right, so next we have what, okay, so if you want to find the equivalent formula of this one, so what you have to do is, okay, by the way, this W, this means unless. Okay, so what you have to do is write the same variables that you have, and then in the middle, instead of unless, you're going to put until. Okay, until, which is represented by the sign U, and then what you're going to do, you're going to put an R, which means not including both. Okay, one of them but not both, and then you're going to put the always property. Okay, so that's basically it. So that corresponds to which letter? So that corresponds to letter C. Okay, that's the answer for this one. Consider a sentence, it is always the case the system remains active until 8 p.m. Okay, for this one you need to translate this sentence into the predicate logic, temporal logic I mean, sorry. Okay, so for this one they have given you that A is denoted by active and T denotes time becomes at 8, and then D is system disabled. Okay, so we have it is always the case. Okay, so this you're going to write it at the end. First, let's focus on what we have for now. The system remains active. Okay, so it is denoted by A, so we write A first. Okay, until 8 p.m. So remember this U, when you have something like this U, this means until, but when you have W, that means unless. Okay, so here we have until, so that means we're going to use U. Okay, U until 8 p.m. So that is denoted by T, so we're going to write T. Or, okay, the or, it remains active unless it is disabled, unless, which is denoted by W. Okay, it is disabled is denoted by, where is it, D. Okay, and then don't forget this, like I said, we're going to deal with this at the end. It is always the case, so you're just going to write an always in front of it. Okay, and so let's see if we have this in the options. So this corresponds to the option A. Okay, so I hope you guys got it. It is always the case that the system remains active until 8. Okay, or it remains active unless it is disabled. Okay, let's move on. Consider a sentence, the process executes unless it throws an exception. For propositional P denoting process executes, Q denoting throws an exception. Okay, so it executes, okay, that is denoted by P, and throws an exception denoted by Q, unless the sign of unless, remember the sign of unless is denoted by W, so that is the case. So that is the option D. Okay, let's move on. Consider the sentence: in the peer-to-peer network, it is always the case that a resource lookup will eventually either discover a payable peer or result in a failure notification. Okay, so here we have R denoting resource lookup. Okay, here and like I said before, we have it is always the case, so you're going to deal with it at the end. Okay, so here we have a resource lookup which is denoted by R, so we're going to write R first. Okay, will eventually either. Okay, so we have either, which means it's going to do one of the options, not both. Okay, so we cannot write this or, we are going to write the other or, which means not both. Okay, because here we're saying either of them. Okay, so then we have oh wait, my bad, sorry, I forgot to write the, because here it says a resource lookup will eventually, so it's gonna eventually lead to it. Okay, so that means it's an implication, because you're doing something and then it's gonna eventually happen in the future. So that means if this happened, then something eventually gonna happen. Okay, so that means it's an if then statement. Okay, so eventually is known as this one. Okay, and then either discover, appear, or result in a failure. Okay, so here D is denoted by discovery. Okay, so we're gonna write D, and then or for the either this one or the failure. Okay, and failure is determined by F. Okay, so that is the correct answer. And then not forgetting the always case, it is always the case, so we can write this in the front, which is the letter B. Okay, next. Okay, so this problem we already solved it at the top. Where was it? Yeah, here. I don't know why did they put it again. Anyways, so the option is A. Okay, so what do we have now? Consider a sentence. Once this task is complete, a writer processes will release the log to a shared resource at the immediately next moment. Okay, so C denoting writer completes his task and R denotes writer releases log. Okay, so here we have writer releases completes its task. Okay, it says once the task is complete, a writer will release the log to a shared resource at the immediately next moment. Okay, so here we have first we have writer completes his task, so that is the first case. And then because once he's done, so it's like if he's done, and then the other thing happens in the next moment, so that's why it's gonna be an if else statement. Okay, if then, I mean, sorry. Okay, so then we have if he completes it, then releases the log. Okay, so which means R, but it's happening in the immediately next moment. Okay, so immediately next moment is denoted by this circle, so that is your correct option then here. Okay, here. Okay, so here we have the car remains as cruise control until and including the moment. Okay, so remember this is very important, until and including the moment. We have seen in the past, okay, here that U denotes until and W denotes unless, right? So we have U as until and W as unless, but what about if we have until and including the moment? So for that we have R, okay, which means until and including. But for this one you have to be very careful, because here whatever you have, like for example if you have a statement written as P and then a statement here, for example, right? So a statement you have P and then you have until and including the moment, whatever, and then you have a statement Q. Okay, so what you're going to write in the temporal logic, you're not going to write like P R Q. No, that is going to be wrong. So for until and including, whatever you have at the end, the Q, you're going to write it at the first, and then you're going to write until and including, and whatever you have at the front you're going to write it at the end. Okay, so you're just going to swap like Q and P, so Q becomes first and P becomes last. So just remember this is very important for until and including. statement. So let's go ahead and solve this. So here we have the car remains at cruise control because this is the P statement. Okay, so remember we're going to write this at the end. Okay, so it is denoted by C, so we're going to write it at the end. And then we have until and including, which is the R, the moment when the driver indicates his intention to obtain the manual control, and manual control is denoted by I. Okay, so IRC. If you write CRI, no, that is wrong because it is written in the form of CRI, right? The cruise control and his intention, no. But since it's until and including, you're going to write the inverse. Okay, so this is the correct answer, not this one. Okay. Okay, so what do we have next? Okay, if a process attempts to obtain access to a shared resource infinitely often, then it will succeed infinitely often. Okay, so for this one, you need to remember infinitely often. You're going to write this as infinity, always, and eventually. Every time you have infinity often, you're going to use this thing over here. So just remember this. Okay, every time you have infinity often, that's gonna be you're gonna put always and eventually together, which is going to be equal to infinity often. Okay, so here if you want to translate it, so if a process attempts to obtain, so attempts, it is attempting it infinity often, then it will be successful infinity often. Okay, so it's gonna be successful infinity often as well, so which corresponds to option E. Okay, next, if a process attempts to obtain access to a shared resources infinity often, again attempt, it is attempting it infinity often. Okay, so then it will be successful at least once. Okay, it's gonna be successful at least once. So here for at least once, like it's gonna happen, eventually happen, right? So that is the symbol that you're going to use. So yeah, just make sure to practice a lot with these symbols and notations because they're gonna be in the exam. So yeah. Okay, if a process continuously attempts, okay, if it's continuously doing something, okay, so which is always, right? So you're going to use the symbol always every time you're gonna have continuously. Okay, so attempts always, and then infinity often. So infinity often, you guys already know how to do it. So what do we have over here? So that is our option B. Next, what do we have? If a process continuously attempts, okay, again continuously attempts, then it will be successful at least once, at least. Okay, attempts and then this one, so that is option D. Next, if at time I either X is true or T is an invariant, starting from time I plus 1, W will eventually become an invariant. Okay, so invariant, I told you at the beginning what is it. So let's go back. So invariant, you just have to memorize that it is the always symbol that we're referring to as invariant. Okay, so if at time X, if at time I either X is true or T is true, okay, so we're saying one of them has to be true. Okay, so this one is true or T is an invariant. So invariant, you know, we write it like this. Okay, so X or the invariant, but it's saying either, so we're going to put this symbol which denotes either. Okay, and next, what do we have? If statement, and then starting from I plus 1, so that, which means the next moment in time. Okay, next moment in time we determine by a circle will eventually become an invariant. So W is gonna eventually become, eventually, remember we're gonna write it like this, the symbol of eventually. It's gonna eventually become, in the next moment in time, it's gonna eventually become an invariant. So invariant W. So W is gonna, in the next moment in time, W is eventually gonna become an invariant. So I hope you guys got it. So this option corresponds to letter B. Consider the following statement: if X is true at time I and the, how do we read this? I forgot. I think phi, no? Whatever, I forgot it. Okay, I is true at time I plus 1, then starting from I plus 1, T becomes true and remains true until and including the time where pi becomes true. Okay, so if X is true at time I, okay, so we have X is true at time I, and then we have whatever this is, phi is true at time I plus 1. Okay, so at time I plus 1, which means at the next moment in time, this is true. Okay, so X is true at time I, and this is true at the next moment in time. And since these both are true, so we can put an and. Okay, so once these both are true, and this is an if and then statement. Okay, so then, so this is if these both are true, then starting from I plus 1, so this is I plus 1, so starting from I plus 1, T becomes true and remains true until and including the time when pi becomes true. Okay, so you guys remember I just told you before that until and including, whatever you have at the front, you're gonna write it at the end, right? So here T becomes true, so T you're going to put it at the end, and then until and including the moment, which is R, becomes true when pi becomes true. Okay, pi. So that's how you're gonna write it. If you write it like T becomes true until and including when R becomes true, no, this is so wrong. So this is your correct option, which corresponds to letter E. Yeah. Okay, so what do we have next? If both of these are false. Okay, so here we have if both of them are false. Okay, so both this and this, they're both false. Okay, so then what we're going to do at time I, then at time I plus 1, then X becomes true at time I plus 1, and it will remain true unless T becomes true. Okay, unless, which is denoted by W, right? Unless. So let's go ahead and write it. So at time I plus 1, so we're going to write a circle to determine the next time, the I plus 1 time, X becomes true, and it will remain true unless T becomes true. So this is how you're going to write it, and this is this corresponds to option number C. Okay, so if this becomes an invariant, this is going to become an invariant in this case. Okay, so here we have this becomes true and becomes an invariant at I plus 2. I plus 2 means second moment in time, so you can write it like double O, or you can write it O squared, which is the same thing. Okay, and it became an invariant. Okay, became an invariant at the second moment in time. Okay, that is if. So then from the time whenever this thing becomes true, so whenever this thing becomes true, then okay, so then X also became true at the same time. Okay, so at the time when this became true, when X became true, at the same time I mean at the time when this became true, x also became true, but at the same time. Okay, so then this is an if and then again. Okay, so then you have if and then again, and because it becomes at the same time when this becomes true, and this becomes true at the second moment in time, right? Because it was because this became true at the second moment in time, and then you're going to write this at the front. Okay, if it doesn't make sense, let me explain again. Okay, so first of all, we have this becomes an invariant at xi plus 2. Okay, so this becomes an invariant at I squared, which is the second moment in time, and because it's becoming an invariant, okay, invariant this. Okay, so I hope you guys understood here. And then because it's an if then statement, okay, so and then from that time, from this time, because it's saying from that time, so this time, right? So from that time, whenever this becomes true, then x also becomes true. So whenever this becomes true, x also becomes true. Okay, so this is basically it what you're doing. So I hope you guys got it. If not, let me know in the comments and I'll be happy to explain. Okay, so we have here our last question over here. Consider the following. This is an invariant, so here this is an invariant. Then from time I plus 1, then from time I plus 1, this will eventually, okay, so this will eventually become an invariant. Become an invariant. It's like a similar question we did here, right? Where did we do it? I think here, yeah. So it's like at I plus 1, it will eventually become an invariant. Okay, so that's how you're gonna do it, and this corresponds to letter E. So that's basically it for this video. And I remember the last part of the exam was all about the UML, so make sure to know it very well, and it was all from the slides, so you guys have to know. You just need to go over the slides and you should be fine. And if you want, I'm gonna make a video on the UML, so make sure to check that out. Okay, so that was it. Bye, thanks for watching.